Hey, hello folks, and thank you for joining us. The aim of today's webinar is to try and cover, hopefully to a useful depth, some of the new data and methods in our latest model build over the US. Obviously, there's going to be a limit to what we can achieve in an hour, but hopefully it'll give some insight into how we approach our work. Next slide, please. My name is Chris Sampson. I'm one of the founders here at Fathom and the CTO today. I'm joined by Dr. James Savage, who is our principal hydraulic modeler, and also by Ollie Wing, who is our chief research officer. Slide. So for those of you who don't know too much about us coming into this, Fathom was formed out of the University of Bristol Hydrology Research Group, which is one of the world's leading centres for research into large-scale flood modelling about 10 years ago. The core aim of our business is to provide model coverage across the entire planet, so we have a real focus on developing models at very large scales. And with our academic background, research really does sit at the heart of our company culture. And on the next slide, thank you, I just wanted to provide a little evidence, I guess, for that statement. So this timeline shows the major publication releases from our group going back to Professor Paul Bates's first description of a raster-based flood model all the way back in 1992. Paul being actually Ollie, James, and my own PhD supervisor, longer ago than I think any of us would care to remember, as well as the company's chairman today. I guess the timeline shows that we've managed to sustain publication output since becoming a company. Indeed, we currently have 5 first author papers currently in preparation or under review, along with multiple co-authorships with external academic partners around the world. However, I think it's worth just pointing out that the academic system is not perfect, and therefore we do try and focus on publishing as we do in top tier journals. So those from, say, the Nature, the AGU, or HEST families. We feel this is worth the considerable extra effort that it takes, as the value of academic publishing is being somewhat undermined in places by the growth of pay-to-publish journals. And these don't really provide much in the way of reviewer challenge. Top journals still do, and so we like to try and put our data and our methods through those in order to get external validation and make sure we're not working in too much of an echo chamber. So I guess that's enough background. Let's move on to the model itself. I think the first thing to say is that this is a ground-up build rather than a rerun of one of our previous US models. And that degree of work and sort of reinvestment is necessary, as there's been really significant progress made, both in terms of the methods and also the data that we have to work with over the last couple of years. Now, much of this progress was integrated into the model framework that we use to generate our new global data that was launched at the end of last year. However, the model over the US is really an extension of this, I guess, and it allows us to take advantage of all of the data richness that exists, I guess, almost uniquely over the US. Next slide, please. So I'd like to quickly highlight some of the product specifications and features, but I'm not going to spend too much time on this, as we've got another webinar next week, I believe, that looks more at the kind of product side of things. But yeah, this will just be useful to give you a sense of the specs of the product before the other guys dive into the kind of methodological details. So we're releasing the data at a third arc second, which is approximately 10 meters. We believe this is a reasonable level of precision given the underlying accuracy of the model itself. We simulate riverine, surface water, and coastal flood. So all of the major flood driving mechanisms are simulated within the model framework. And we're able to provide views for any climate scenario out to 2100, so long as it falls within a 5-degree temperature rise since pre-industrial. So there's really a lot of flexibility within this framework for forward-looking views. And this differs really quite significantly from anything we've done in the US before. There's been a lot of work done by the USGS as well as individual states on LiDAR collection over the last few years. And therefore, a lot of the work that's gone into preparing data for this model has been around that particular piece. Sorry, if it could be possibly, yeah, thank you. And as you've just been previewed, James is going to talk about that in some detail in a second. We provide the data as return period depth layers and also as what we call risk scores. The risk scores take two forms. There's relative risk, which is an annual average loss layer calculated using an assumed uniform exposure, and risk category, which then takes this risk, the risk layers, and categorizes it onto a 1 to 100 scale, which includes information about locations that fall just outside of the simulated hazard layers, but might still be at risk given model uncertainty. So those areas that are proximal to the model maximum flood extent. Finally, before I hand over to the others, I just like to highlight that we put a lot of work into data accessibility as well. So we've now got a very performative API that gives sub-second response times for location level queries and also allows querying by shapefile. We've also got an asynchronous portfolio mode, which allows you to upload a file containing millions of locations and get the results back from that. We specify it to be within an hour. Actually, it's testing to be much quicker than that. It's often delivering those returns within a few minutes of download. So yeah, there's a lot of work that's gone not only into the model, but also actually enabling everybody to access that information and make use of it. So with that, we can move on to the next slide, and I'll hand over to Dr. James Savage to talk about the trade data work that we've been doing.
Thanks, Chris, and hey, everyone. So yeah, accurate terrain data is really crucial for flood modelling, both in terms of representing localised water depths, but also for accurately simulating the propagation of floodwaters on the floodplain. And as Chris said, one of the main technical advances we've made with the US flood map has been the creation of a new terrain dataset, Fathom Plus, covering the US. So we found that there were significant amounts of data missing from pre-existing national level maps, but we also saw an opportunity to incorporate our own data, Fathom, into areas where LiDAR was missing in the US. For those who don't know, last year in partnership with the University of Bristol, we published Fathom, which is a 30-meter global terrain model based on a 30-meter Copernicus digital surface model, but with buildings and forests removed. And so what we've done is we pieced together all the LiDAR data that we can grab within the US and obtained, processed, made appropriate datum corrections, and blended together both between LiDAR datasets and with Fathom across the US, which was a significant amount of work, but hopefully the following examples justify the time taken to do this. So yeah, we've got some maps to show you. So the one on screen at the moment shows the LiDAR coverage that we had when we previously modeled in the US. And you can see that there's large gaps across the US with, I think, less than half of the US covered. If we go to the next one, fast forward to present day. So this is our current LiDAR coverage. And you can see there's significant increases in coverage. And if we overlay the two, we can see that not only has the extent of LiDAR been increased, but there are many areas where LiDAR has been updated since we last modeled in the US as well. So where LiDAR has been reflown, for example. And as we mentioned, the remaining areas are now covered by Fathom. So this has allowed us to significantly increase our LiDAR coverage across the US. And we've got some great stats on the screen to show this. So I'm not going to go over all of them. They're there for you to have a little look at. But some of the ones that jump out are that the amount of LiDAR in our US flood map has doubled since 2020. LiDAR now covers 79% of the area of the lower 48 states. And 94% of the buildings in these lower 48 states are now covered too, compared to only 58% previously. So it's a significant increase in assets which are now covered by LiDAR within our US flood map. So alongside the terrain, another really important aspect of flood modelling is to have an adequate representation of both the location and the size of river channels. So we use NHD Plus to represent the location of river channels, but the more difficult part is determining the bathymetry of river channels to correctly convey stream flow. A couple of years ago, through work with the researchers at the University of Bristol, we published an approach hereby we called the Channel Solver to estimate the size of river channels for any river in the globe. And this was published in Water Resources Research in 2021. And the key concept here is that river channels are sized to convey a bankful discharge as calculated by our regionalised flood frequency analysis, which I'll go into further in a minute. And this kind of diagram on screen kind of gives you a bit of a flavour of the bits of data that is involved in this. But what it does is it takes the bankful discharge, it takes an estimate of river width, which we take from observed data where available, and an estimate of bank elevation, which is taken from terrain data, and it solves the gradually varying flow equations to estimate the bed elevation. Now, previously, this approach assumed that rivers had a mild slope, which is true for the majority of river channels. However, the approach has now been extended to handle additional flow profiles for different slope conditions. So As you can see on screen, we've got steep slopes, critical slopes, horizontal slopes, and adverse slopes. And what this allows us to do is allows us to make a better estimate of the water height elevation. And when combined, a better estimate of the water elevation, a bed elevation. And what it means is that the behavior of the channel solver becomes much closer to the dynamic behavior of the hydraulic model that we simulate within our model, within our US flood model. And this results in better bathymetry estimations, which feed directly into our fluvial, pluvial, and coastal models. So we should have an animation showing a simulation in Memphis that should demonstrate the importance of this. So here we've got an inflow boundary at the top. The river water flows through along the river channel, and we start at the bottom of the screen to see backwatering effects as that kind of flow of water reaches meanders, which slows the water down. A water back flows out, spills out into the floodplain, and it starts to flow into some of these relic meanders, which are captured within the terrain model. And we can also then see the main flood wave come down from the top and join this as well. So it really shows how incorporating these rivers correctly can result in has a big control over the flow profiles that happen within the simulations. So that's hopefully showing the importance of both the terrain and river channels and how we incorporate them within our hydrodynamic models. Another really important aspect to modeling is the boundary conditions. So how much flow are we putting in the model? So for the fluvial model, we use a regionalized frequency analysis, as I mentioned earlier. So this approach allows us to take gauge data as well as various local catchment characteristics, such as upstream area, rainfall, and slope, and use this to estimate flows in ungauged areas that exhibit similar catchment characteristics. And so this is something we developed over the last few years, recently incorporating machine learning methods to better link catchment characteristics to extreme flows. And the plot on screen shows the performance of the RFFA. So on the x-axis, you can see the observed peak flow, and on the y-axis, the model peak flow. And you can see that with this split sample validation, the models perform well, particularly for the higher flows that start to cause these flood events. And again, this is based on published research as well. And on the next slide, we've got an example of a fluvial output. So this is just a 1 in 100 year fluvial undefended map for Houston. And again, we can start to see some of the detailed flow pathways being picked up in these flood hazard maps. For our pluvial model, we take rainfall intensities from the NOAA Atlas 14 dataset. And what we do is we simulate explicitly the 1 hour, 3 hour, and 6 hour rainfall events for a range of different return periods within the hydraulic model. And again, this is another example for Houston. So this is a 1 hour rainfall simulation for a 1 in 100 year flood event. And again, you start to see the key flow pathways being picked out along streets, and smaller river channels as well. For our coastal model, we undertake a regionalized frequency analysis that combines global models with local coastal gauges to estimate extreme water levels along the coastline. And so this is an example of the 1 in 50 year extreme water levels along the coastline. And what we'll do is we'll apply a surge profile on top of this and model the propagation of floodwaters inland within the hydrodynamic model. And we've got an example of this as well. So yeah, this is a large flood event in Miami, a 1 in 1,000 year undefended example. Again, showing the high resolution terrain data really coming out in this. So another thing we've done is we've incorporated the NLCD data. So we've used this to identify urban areas, and we use this to define urban drainage standards within our pluvial model. We also extract buildings data from the Microsoft Buildings dataset to identify the locations of buildings. And we then combine the two datasets to define spatially variable Manning's friction coefficients, which we use within the hydrodynamic model. So yeah, that covers some of the bigger changes that we've made to our hydraulic models since we last undertook modeling in the US. So I'll pass over to Ollie now to discuss flood protection, our climate dynamics framework, and also some validation data.
Thanks, James. Hi, everyone. I'm the trigger happy slide changer, so hopefully it'll be a bit smoother moving forwards now. Yeah, I mean, we obviously can't talk about US flood mapping without talking about defenses. These are some of the most heavily engineered rivers and floodplains in the world. So I'll just take you through some of the new methods and data we've been using to represent these protection levels. So firstly, we take the obvious data set, I suppose, which is protected areas from the US Army Corps of Engineers. So these are polygons that the Army Corps defines to be defended, associated with a certain design level, and we use that as a post-process to our flood map. So what we're showing here is the undefended simulations that James has been talking about, where we essentially have no representation of defenses in the hydraulic model. But then when we apply the defense standards, for instance, here's some polygons representing a 100-year flood defense in this bit of the mouth of the Brazos in Texas. We essentially just mask that all out. Now, the reason we do this as a post-process, we've tried many different ways over the years, incorporating it directly in the model, masking out areas in the DEM, or whether we change the bankful discharge in the river channels, all sorts of different ways. But for this, we choose to post-process it because of the level of uncertainty involved in how defenses perform and where they're located, and how those performance standards might change as the climate warms. It's much easier for us to do some GIS work, in essence, on these layers and explore the uncertainties, adjust defense standards where we think they're not validating particularly well, or indeed incorporate new data. So this one's quite a simple one. We've got a 100-year flood, 100-year defense, the water gets masked out. What we do above those design levels is permit overtopping. So previously, we would essentially assume an undefended state above design standard levels, but that leads to huge step changes in the flood map. So for instance, our 200-year here might end up looking, just like an undefended 200-year map and be a total catastrophe within this defended area. But what we do in our defended maps is basically calculate the marginal discharge between the design flood and the design standard of that levee, and work out within that polygon how much water essentially to put in it. So you end up with much more gradual changes across return periods, which can really help when it comes to loss modeling. You don't get these huge jumps in risk from one return period to the next. Of course, these databases are woefully incomplete. And so you've got to do something else for all of the areas that don't have any information available. So one way or another, you're making an assumption. You can either assume that anywhere without any information is undefended, which is essentially what we previously did in our US modeling. And so an example of that is here. We don't have any defense information for this residential development here in Florida, just obviously picked at random. And so everything is behaving as if the channel and floodplain are in a largely natural state. So probably the river will exceed bankful discharge every 2 years. And so you'll start to get quite a lot of inundation at frequencies surrounding that. So we've got a 20-year flood here, absolutely devastating this community. And because there's no defense information, is it because there aren't any defenses, or is it because they're missing or not recorded in any coherent database? So one assumption is we just use the undefended model here. The other assumption is that we link design standards to different levels of urbanization across the US, so that when rivers are flowing through relatively urbanized areas, we make some assumptions that the degree of urbanization is linked to a design standard. So there's obviously a lot of uncertainty involved with doing that, but it means, for instance, here at your 20-year level, you're not getting any floods in this particular area. And even once you start to get to that 100-year level, because of that overtopping logic, you're still not seeing even the extent of that undefended, theoretically smaller flood. And so there's a lot of uncertainty associated with defenses in the US. So we actually offer all sorts of different maps, because this is cheaper than a full hydraulic rerun each time for every different defense state. We can provide different views with different defense assumptions that users can then tailor to their specific use cases. Potentially in the engineering community, they might just be interested in known defenses and not have any of our additional assumptions surrounding that. But maybe in the insurance loss modeling case, you'd be much more interested in potentially more realistic estimates of defense standards in the absence of data. And then the undefended models, you might use to essentially explore what if these defenses didn't perform as we expected, or weren't there at all. Another hugely important advance in this mapping program that we've gone through is the incorporation of dams. I mean, dams are everywhere in the US. There's virtually no major rivers without them. And so it's pretty unrealistic to expect a good representation of flood hazard without thinking about how we represent dams. So in this example here, again in Texas, there's a dam in the lake to the very north. That very hot pink lake up the top has a dam on it. And this is, again, what the undefended hydraulic model spits out when it comes to our 100-year fluvial flood here. Now, we've devised a machine learning method that essentially predicts how much a given dam will reduce different types of floods. So in essence, we'll look at the inflow to each dam in the US, we'll look at the outflow, time series of these things, of course, and work out how much the outflow has been reduced, proportional to the inflow. And where we have dams that don't have all that information, we essentially use the characteristics of dams that do to predict what might be going on at every dam. So obviously the main one there would be reservoir capacity, but all sorts of different predictors go into that. So that at each dam we have an estimate of how much extreme flows might be reduced. And again, it's treated as a post process. So you can see here we've reduced the flows coming out of that dam from the north of the domain there, and had a much smaller flood extent as a result. And we don't do this by resimulating the hydraulics. We essentially look at what the new return period of the dam reduced flow would be and work out where we've already simulated it. So everything that I'm talking about really relies on having a very wide and dense inventory of loads of different types of floods. So the work that James was telling you about shows you floods from the 2-year level all the way up to a very uncertain but theoretical 10,000 year level. And we deem that to encompass every possible flood, whether defended or in different climate states and stuff like that, that we then interpolate out different defense scenarios from that. When it comes to climate dynamics, this again is a relatively it's not a relatively major update, it's a huge update for us. We've spent many years refining our climate dynamics framework so that we can, again, take those undefended maps representing history and update them, whether that's to the present day or some past historical climate or any climate projection out to 2100. So again, what James was talking about is all observation-based. You know, we're looking at historical river gauge data, we're taking the NOAA Atlas 14 data, which isn't updated to the present day, and using climate models to update that. So our sort of present day view of risk is a 2020 centered climate state, for example, where we'll have taken the information from climate models, worked out how much rainfall, for instance, in the NOAA Atlas 14 case, might have changed, and updated the return periods in the map accordingly. But before we get onto any of that detail, we first got to contend with the scientific reality in many ways that climate modeling is not made for us. It's not made for flood modeling. It's not really made for risk modeling or understanding of extremes or anything like that. The things that these models are really good at is telling us about averages of averages of averages of averages, the very opposite thing that we care about. You know, we're talking about slow moving variables like temperature, how they might change at continental or global scales, and indeed average temperature at that. Completely the other end of the spectrum is where we sit. We're interested in transient and local extremes. And so before you even begin to start taking climate model information, you've got an enormous gap to bridge there. Also importantly is that when you look at the performance of these models in representing key flood generating variables, rainfall is the obvious one, they have known deficiencies because the grid scale might not be sufficient enough, and important processes like convection won't be simulated within the model, but parameterized instead. So because of this, we don't really take much use or take much notice of the intensity values that come out of climate models. We know that the rainfall at a given point in time in these projections is not going to be useful in terms of determining future flood risk. Instead, we look at the relativities in these models. So we'll look at what's going on at a given level of baseline warming, and how much does that change in a relative sense at a given point in the future. And we then link that to what we deem to be more locally relevant flood predictions from all of the work that we've just outlined. So in effect, you'll be perturbing the boundary conditions of our models in a proportional sense based on the output of these model cascades. So the first, I guess fairly obvious one is fluvial change factors we take from global hydrological model cascades, which take global climate model data and work out the river flow response to them. And this is essentially a subset of the global climate change factors that we use. It's climate is global. You'll need global models to make these kind of predictions. If you use regional models, you of course need the global models at those boundaries anyway. So we take a global view of climate change from the data set outlined there and look at the relative changes in annual maximum flows per degree warming. What you can see on the map there, I mean, we've got a horrendously extreme scenario just to show you how big the changes could potentially be in some of those very warm worlds. The relative change in flow, where it increases, we have very dark greens, and where it decreases, we have browns. But just as importantly, the places where we have all of this cross-hatching is where less than 3/4 of the models agree on even the sign of the change, let alone, what the relativity is. They can't even agree on whether it's getting wetter or getting drier. So this is really important information that is needed by the user and is going to be needed when it comes to producing climate condition flood maps. And I'll go more into uncertainty in a later slide, but just to go through each data source, fluvial is a bit more coherent and consistent, aligns with basic physics, really, that a warmer world will be a wetter world when it comes to rainfall, and particularly extreme rainfall. So much more consistent wetting signal, again, for an extreme scenario of 4 degrees, and potentially some drying in the southwest, but you can see those are areas where there's a lot of uncertainty as well based on that hatching. When it comes to coastal climate changes, we look only at mean sea level change, and this is from a huge number of different models and emulators that were part of the IPCC's 6th assessment report. Again, I picked a massive scenario just to show you some big scary colors, and you can see the mean sea level change all across the US, again, drawn from that global model, but some pretty big increases there in the Gulf, for example. So on uncertainty a little bit, we're not deterministic about a given warming level or a given climate scenario is never just a single change factor. We have distributions of change factors based on all sorts of things. The first is that we have uncertainty around how much warming is in the baseline model initially. The historical period could be anything from when the first river gauge was installed or all the way up till now. So we don't treat it as a single fixed point in time because we use all sorts of historical data of many different vintages in the model. So we allow that to vary based on the recording periods of the river gauge data, the tide gauge data, and the NOAA atlases, for example, to work out a distribution of possible warming levels in those historical maps that are directly simulated. And then we convolve that distribution with the distribution of change factors that are taken from the models. And these represent all sorts of uncertainty. The model uncertainty itself, obviously when we're using river flow change factors, there's uncertainty in the hydrological models. The coastal models have uncertainty in as well. And there's also some inevitable variability within those that we haven't been able to remove, even though we've tried to focus on those average changes absent of variability. So that means that for any given scenario, you can look at the median, but if you were to look either side of that as well at maybe some of those more extreme percentiles to work out the uncertainty in these tools, you might see completely opposite flood maps from the lowest percentiles to the highest percentiles, reflective of the levels of uncertainty and how floods might be changing. So how we apply that, again, I've sort of gone over this, but we take those change factors and we apply them onto the baseline flood frequency curves that we simulated the model with. So an example here is that a 100-year flood is now 20% more intense when it comes to magnitude. And that ends up looking a lot like the 129-year flood that would already be encompassed within that dense inventory of flood maps. And so we can then interpolate out our future 100-year flood by interpolating between the 100-year and the 200-year flood, for instance. Now, the way that works is on this horrifically busy slide here. If you just ignore the bottom bit, that's just to show how different tributaries are processed together. But if you just focus on the main stem, we've got the representation of a 20-year flood there, and we've applied a change factor of 31% for a given warming level. And that then looks a lot like a 55-year flood if we look at the flood frequency curve. So you can then, as we move to the middle part of the slide, we take our 50-year flood and the 100-year flood, because those are the return periods closest to that are simulated. And we essentially weight each pixel's flood depths depending on the proximity of the intensity to the 50 or 100-year flood. And importantly, we don't just look at wet pixels when doing that. We have all these green values in the middle there reflect negative depths conceptually. So look at the height of each point above the nearest flooded surface, so that your flood extent can grow or shrink when you are interpolating. And the bottom side there shows that this is done individually for each river reach in the country, and then merged into the main stem at the end there. Now, fluvial is the most complicated one of those, but pluvial and coastal take much a similar flavor in this sort of interpolation routine. So in summary, the fact that we are putting a lot of the heavy lifting in the functionality of these maps into post-processing rather than direct hydraulic simulation gives us and users, of course, massive amounts of flexibility in the types of data they might want to interact with. So all of these things listed on the slide here are variable. You can pick different uncertainty levels, any different climate scenario, any defense state, any return period. The list goes on, because it's a rapid resampling of hydrodynamic flood maps. Now, I must disclaim this slide is preliminary. We'll be going into a lot more detail on validation over the coming months, and as we have done with every single model we built to date, exposing it to peer review in good quality hydrology research journals. But some of the initial results of this exercise are really promising. So what we've done so far is taken engineering grade flood maps where they exist. So FEMA is the obvious one in this case. They don't exist everywhere, but we'll take the high quality ones where they do, the AE and BE zones, and compare our flood hazard maps to those where they exist. We've also taken data from the Iowa Flood Center, which is fairly self-explanatory in that they map flood hazard across the state of Iowa to very high fidelity, and also release the data at different return periods. It's somewhat, I shouldn't say easy, but it's somewhat easy to get the very extreme events right, because in most cases you're just filling floodplains up, and even simple models might be able to just fill up a valley up to its sides. And when it comes to comparing the patterns in the flood extent, get quite good scores, because a lot of the very easy to predict wet pixels are therefore correct. But when it comes to higher frequency events, maybe a 10-year flood, for example, these generally aren't confined by valley sides, and so are much more sensitive to microtopography, much more sensitive to the channel solver, for instance, and this is really where the quality of the model can start to shine. So the plot here is just a random selection, really. The eagle-eyed amongst you might recognize this is the Ohio River, and that confluence there is Pittsburgh, Pennsylvania, and the greens are where we agree in this case with FEMA flood maps in this area. The yellow is where we are under predicting relative to FEMA flood maps, and the false positives there in pink show us over predicting relative to FEMA's flood maps. And if you look at the various results, I mean, those are kind of as good as it gets. If you're going to get scores higher than that, the critical success index balances these over and under prediction errors and gives you a fit to the benchmark data out of 1. you're just going to be rewarding noise in essence. If you go any higher than that, the benchmark data aren't good enough to warrant a perfect match. But we can see, particularly for the very high quality mapping in Iowa, a really good correspondence with our new model there. The previous work we did in the older version of our US maps, they're still good, but we are seeing a pleasing improvement with all the work that we've done here. Again, one example here, you can see that model was a little over predictive in this area here, principally because of all the dams along the Allegheny River there, meaning that we're a bit over predictive in the previous model where there weren't any dams, and now there are. And equally, looking at our global flood map, which is not the topic of this webinar, but just to see the enhancement you get from using US specific data. I mean, the global map still does pretty well for a region like this, but again, not quite as good in this image in particular, a bit dry perhaps, but overall, pretty nice scores all round. That's all I'm going to say. Back to Chris.
Thank you, James. Thank you, Ollie. Got through that reasonably quickly, given the number of slides, so well done. So I think I'll just kind of round up the presentation here with a few conclusions around the model. As we've demonstrated, I hope, it's a ground-up build that really does try and make use of the rapid progress that's been made by ourselves and by research groups around the world in terms of data and methods for large-scale models. They genuinely are getting better. They'll continue to do so, and it's exciting to see both in the US and globally what we're able to achieve with data and computing and rigorous testing of these frameworks. LiDAR coverage is critical. The US has some of the best coverage in the world, and that work is also ongoing, and we've therefore done our best to incorporate it consistently into the modeling framework. And that's not easy to do because so many of these collections haven't yet been standardized and incorporated into the national map, and so you've got to very carefully handle each one and ensure that you know where your datums are, that you are regridding properly and everything is aligning, because a hydraulic model is a very good way of highlighting any errors in your terrain processing very quickly. So a lot of work has gone into that. As Ollie's just talked through, this has yielded improved model validation metrics. And as much as one can validate constant return period in space, large-scale models, a lot of that work does rely on model-to-model comparisons, where you're comparing these types of models to local engineering models. And of course, as all models have uncertainty, no model is true. You're never looking to achieve a perfect fit, but the recently executed FEMA models are very strong, and the Iowa Flood Center do great work. So we feel they are really valuable benchmarks to test a framework like this against. The climate dynamics framework has been conceived both in the US and globally to really allow users who are interested in examining how risk might change in the future to have that flexibility, to be able to play with scenarios, to not be forced to work with a prescribed scenario, and to try and understand which areas are most sensitive. And I think sensitivity is key to trying to understand how risk might change, because of all the uncertainties, the myriad of uncertainties that exist when attempting to pin down what might happen in the future. But if you know which areas are sensitive, then you've got a pretty good idea of where you need to be focusing your attention. We tried to make the data as accessible as possible and usable as possible for as many range of users. So we have the classic return period depth maps that most people, I suspect, on this webinar will be used to using. And we've also attempted to do some processing on top of that to make the data more easily usable for specific use cases via the risk scores and layers, and then putting all of that information onto an API service to allow easy sort of sub-second querying. We also work with a number of partners and resellers who you may also already be working with, so there's facilitation potentially in that direction. Or for those of you who like to handle large amounts of data and process it in-house, we can also license the data to be housed on premises within your organizations. That's also possible. So with that, I am going to finish the slides. I'm going to ask in a second, and I don't really know what I'm doing, so I hope this works, but we have a little poll. So if you wouldn't mind answering the questions that are about to, I hope, pop up on your screen, we would appreciate it. And in the meantime, I will kind of open the floor for questions. So yeah, please, if you wouldn't mind answering the poll questions, and also start to tap some questions into the Q&A, and either Ollie or James, or in the worst case, myself, I suppose, will attempt to answer some of them for you. So we'll start doing that in a minute or two. Thank you very much. Okay, folks, I'm going to start by answering a question from Curtis Smith. I also just want to ask Ollie and James whether they can see the questions that have popped up. You can? Okay. So I'm going to answer, how long does it typically take to simulate one event for a given watershed based on some unit of area? So I think it's worth noting that we don't, within the framework, simulate one reach at a time on an individual basis. Instead, we split the domain into quite large simulation tiles, and then try and decompose those into reaches that simulate as many reaches simultaneously that don't interact as possible in the name of computational efficiency, because obviously the US is a large place. The runtime of the model is therefore determined really by the largest reach that you're simulating. But to give you an idea, simulating a sort of 100 kilometers or so along the Mississippi may take an hour or two. It's that kind of order. Whereas if you are simulating very small streams, that simulation time will be just a few minutes. And that's a combination of how many wet cells there are in the domain, and also the length of the hydrograph that you need to simulate to actually be able to represent the kind of floodplain dynamics. Obviously, on the Mississippi, you have a very large floodplain, and you need to give the simulation time to actually reach maximum extents and maximum depths. So that's that one. James, would you like to answer the question from Tad Hansen?
Yeah, so there's a question asking what resolution the model's run at. So the model is run at 30 meters resolution, and that is in our fluvial and coastal models. And then we downscale that to 10-meter resolution.
So we have another question here from Shane asking, will the map comparing US3 and FEMA data be publicly available? So as Ollie says, we will be doing a bunch of work on this over the coming weeks and months, and that will ultimately find its way into publication. So there will be maps and statistics available that do that comparison. Exactly what they will look like, obviously we haven't written the papers yet and produced the figures, so I can't tell you exactly what they'll look like, but if you look at the various publications we've produced in the past, you should get a sense of the types of analytics and data that we'll provide along that way. And obviously, as that will be in the open peer review space, and we do ensure that the journals we publish in are openly available to the public and not sat behind paywalls, you will be able to get access to those answers. So hopefully that gives you the information that you need. got another question here from Jonathan asking, is the FabDem Plus US data set available to the public? So we do share FabDem with certain research institutions. So it depends really whom you're working with. However, FabDem Plus, in terms of commercial users, is commercially licensed. So if you would like to use that data for commercial work, then we do license it, and I'd ask that you get in touch with us and we can have a conversation around that. James, you've volunteered to answer a question from Eric.
Yeah, so Eric's just asked if we use a mesh with our hydraulic modeling. So we don't use a mesh, so we use a fixed resolution across the domain. Quite an easy question.
Ollie has put his hand up to answer a couple of questions actually, one from Kurt and one from Aaron. So I'll let you take that away, Ollie.
I can volunteer to answer them, so that's fun. I'll start with Shane's next one. What is the vintage of the National Levy database that went into the US model? It's from this year, so downloaded that from the portal this year, which I hope is a sufficient answer to that one. Kurt's asked, how was this work funded and how does it fit in with the national water model? The first one is that it's not funded publicly in any sense. It's from all of the money we make off our clients through licensing. So this isn't publicly funded work at all. So we're a commercial operation. We just work very closely with public sector and academics and so on. But yes, if our careers might have taken a different turn if flood modeling was adequately funded publicly 10 years ago, but still not really in a state where it is. When it comes to the national water model, it's not linked at all to the national water model. We did do some early work with that framework quite a few years ago now when it first came out, forecasting and hindcasting Hurricane Harvey, for instance. We used the national water model to look at what the return periods in our flood map should be to represent that event, for instance, but otherwise there's absolutely no association with it whatsoever. Another one while I'm here, Aaron's asked, do the data come with risk scores and centimeter depth information? Yes, they do. So the depth information is pretty standard. Just to be clear, the format is such that each pixel has the depth of flooding in centimeters, mostly for storage reasons, so we don't have loads of floating point numbers. It doesn't mean that it's a prediction that's accurate to a given centimeter. It's just how the data are presented. And yes, the new thing that we've presented that Chris outlined briefly is an assimilation of all that depth information into much more consumable data types for anyone who wants them, really. So, for instance, we'll produce a relative risk layer that integrates with some uniform vulnerability functions. Just integrates all of that depth information, converts it to a damage, and computes essentially what an average annual loss would be using all of that information, and then that's classified in the risk scores. So lots of flexibility in terms of how you want to consume that data.
Unmute myself. Thank you, Ollie. Michael has asked, which areas are complete? Is Florida? ? I suppose you're asking which areas have we completed model execution on. The answer to that is everywhere. So this isn't a proposed model framework or an area that we sort of execute based on client demand or anything like that. The model has been run, so we have full coverage across the entirety of the US. The only exception to that is that we haven't run explicitly within this framework all of sort of rural Alaska. That is covered by the global model, but we haven't run it all in this framework, given that it is largely unpopulated, particularly as you go to the extreme north. I've got a question at the top here from Brett. Do you have any validation results for pluvial flood mapping? So that's quite an interesting question, because there is no clear definition within the model of exactly where pluvial becomes fluvial, I suppose, in terms of the final output results. When you look at them, we obviously have a rain on grid model to simulate pluvial, but that rain on grid model includes the river channel network and subgrid rivers, and therefore those rivers will start to flood in the pluvial model, and therefore the pluvial model drives what might be termed fluvial flooding in very small channels, and therefore there is validation of those smaller channels in some areas, be they with the modelling that I was done or in certain FEMA models that cover smaller channels, and so that you could absolutely count that towards validation of pluvial modelling. In terms of a more systematic assessment, once you're away from the channels, that's really quite difficult, because we don't have an awful lot of sort of standardized return period maps against which to compare those models. So then you are left to look at the performance of the model against observed footprints, and then you have to make an assessment of what the return period is that you should be checking. We have done some work over the years looking at simulating observed events using the framework or various variations of the framework, and comparing the simulated results against the observed footprints. So Hurricane Harvey is a classic example of that, to give you an indication of how well the model can do. But it is certainly true that the pluvial model is more uncertain than the fluvial model. Fluvial flooding is controlled by very local topography, lots of local features, whether or not the local drainage network, or firstly, what is the capacity of the local drainage network, and secondly, what condition is it in, whether there are blockages, because there very often are during extreme storms. So it's a tricky picture when it comes to validation of pluvial behaviour within these large frameworks. I don't know whether Ollie or James has anything to add to that. Really, it's a good question.
No, I don't, except we spent many years tearing our hair out what's left of it over the arbitrariness of the definition, and it becomes very difficult to test these things in isolation. And so at least for these grand national scale comparisons, putting all the perils together and comparing it seems to be the fairest way of getting some measure of skill. So yeah, it would be a case of going event by event and looking at observations and high water marks, but that data's fairly scarce for true pluvial events in urban areas. So not easy.
Not easy. Yeah, thanks. James, you've got a question from Jeff Kratz that you would like to answer?
Yeah. So Jeff's asked whether the Caribbean coverage was contained within our global model, and the answer is yes. So our global model covers everywhere across the globe. So yeah, the full Caribbean land area region will all be within our global model.
Okey-dokey. Ollie, you have put your hands up for a few more questions that popped up.
Yeah.
So I'll let you answer those in whichever order you want to, I think.
Okay. We'll start with Chiranjib's question on, do you store the footprint by events or by return period maps and then reconstruct the events by back interpolating the depth to the associated CDF? It's a great way of putting it. It's the latter. So the hydraulic model doesn't simulate events in the conventional sense of them having a spatial structure with varying return periods. It simulates a given return period simultaneously. Well, the model itself isn't simultaneous, because you get all sorts of horrible interactions at tributaries that skew the probabilities, but the resultant map just shows you the probability of exceeding a certain depth. So those are all stored within spatial units. Maybe it's river reaches or sub reaches. I mean, it's all arbitrary what you call those things, and the interpolation is done on that basis by looking at how those return periods have shifted. So I mean, the ultimate point really is, if you looked at the present day maps, you'd find theoretically every flood that could possibly happen, and all of the various conditioning on top of that is a frequency shift in space within those maps, is the easiest way of conceptualizing it. Trevor has asked, how do you consider levee failure and dam break flood? And then a slightly different second question, so I'll focus on the first one. Well, we don't consider those explicitly, at least for levee failure. Potentially our undefended maps are something of a proxy for failure. I mean, we don't simulate specific points of failure or even its likelihood. And in the risk scores, we do incorporate some fragility curves to weight between the undefended and the defended models when it comes to generating that average annual loss proxy. So for instance, the bigger the difference between the design standard and the design flood, the more likely you are to sample from the undefended map rather than the defended, for instance, but nothing explicitly in the hydraulics. When it comes to dam break, there really is no representation of that at all. I mean, maybe in some cases it's analogous to a 1,000-year defended flood, but I'd expect that to be very rare. We do some bespoke dam break modeling, and we have done that in the US for quite a few dams, but it's entirely separate to this hazard map. The next part of that was, do you see a decrease in climate change scenario flood maps for certain areas as well? Yes, absolutely. You saw some of those change factor maps. For pluvial and coastal, the signal is pretty consistent in I say a positive change. It's not remotely positive, it's increasing hazard. But for fluvial, you see a very mixed picture. You know, it seems pretty even. Places where fluvial floods may decrease in a warming world. But of course, you saw all of that cross-hatching, how much uncertainty there is in those predictions, that generally speaking, if you were to look at quite an extreme percentile, maybe the 75th or something like that, of the uncertainty in those maps, potentially all of the fluvial ones would be positive, and all of the very low, maybe 25th percentile maps would be drying, and then the median somewhere in between. But yes, this is not to say that there's any fixed embedded assumption in everything getting wetter as it gets warmer. We just follow the relative changes from these climate model cascades. The other one, which I've stupidly volunteered to answer, is one of Jonathan's on what coastal dynamics are incorporated into your coastal modeling, i.e. storm surge or tsunami dynamics or bathtub model. Yeah, it's not my area of expertise, but just because bathtub triggers some response in me that I can't control. We don't do any bathtub modeling here. Everything is hydrodynamic. Particularly at coasts, bathtubs are practically useless because they just propagate flood waves infinitely inland if the elevation data allows, irrespective of if there would be the momentum to carry them that way. So no bathtubs here. When it comes to the coastal modeling itself, we start at the shore. So the regional frequency analysis that James is talking about is predicting the boundary conditions to our hydrodynamic model. So everything out at sea is captured by those statistics, as it were. So we represent tides and storm surges and waves in the boundary conditions to that model, and those are propagated inland, just like the pluvial and fluvial models work in terms of solving those derivation of the shallow water equations. So I hope that was an adequate answer. I don't know if anybody else has something to add. Good.
Well, yeah, we're also almost out of time, so I was going to quickly answer one more question from Aaron, which is just to ask whether the Pacific coast is now included. Yes, it is. And then James has also put his hand up to just answer a bit of a question from Kurt around the potential for forecasting. Yes.
Yeah, maybe not such a quick question, but we'll go for it anyway. So yeah, Kurt's asked about whether this model could be used to provide real-time or close to real-time flood maps. So this is something that we're doing in conjunction with the UK government. particularly in less well-developed countries where we've been kind of using data from our global flood hazard maps and taking forecasts from GLOFAS of return period forecasts along river sections and interpolating what that flood hazard map might be for that given event from our pre-existing hazard layers, and then using that to understand populations at risk. So it can certainly be used in that way. And it's something that we're looking to develop further.
Yeah, it's certainly an interesting area. Forecasting is really challenging, as everybody I'm sure who's ever had a go at it knows, because of the uncertainty and the boundary conditions as much as anything else. But inherently, these kinds of frameworks, with just a little bit of retooling, do lend themselves to it because of the way they're constructed, because they're designed to handle data uncertainty, because they execute quickly, because they build in a largely automated manner. All of these things lend them to potential application within a forecasting framework. And then you can play with different uncertainties. So you can either decide that you want to spend a bit more compute, be a bit more deterministic, and actually run the hydraulic simulations explicitly, but you probably can't run that many realizations. Or you can use a retooled version of the sampling methodology that Ollie's talked about a little bit to start to really explore uncertainties within the forecasting, the atmospheric forecasting that's coming through, the precipitation forecasting that's coming through, for example, by building hazard maps without actually executing the hydraulics, using the post-processing type methods, and then you can have a real look at uncertainty. So there's a lot of research being done by ourselves and by others, of course, in this space, and I think there's potential here over the coming years to really see an improvement in our ability to forecast flood footprints at very large scales. Thanks everybody for hanging around. Most of the people who joined this webinar at the beginning are still with us, so that's really nice to see. We obviously either everyone's fallen asleep or you decided to stay. Thanks for the engagement, loads and loads of questions. As ever, you know where we are. Please do get in contact if you'd like any more information about this. Keep an eye on our social media channels and our website, because we talk about all the events that we're doing, the webinars that we're giving, the papers that we're publishing, and obviously the services as well that we have to offer, because as Ollie answered earlier, we do need to fund all of this work somehow, as we don't get lots of public funding. So let us know. Other than that, have a great day, and thanks for joining us.
Thanks everyone.